Hello, Calculus and Vectors class. This is 6.6 Exponential Models. This is our very last lesson of the Calculus and Vectors course. We're just going to do a bit more practice with exponential functions, and we're going to try to apply it to some other types of problems that hopefully you've seen before in either grade 11 or advanced functions or physics. And we're going to see if we can use a bit of know-how to help us learn a bit more about how these exponential functions operate, especially with their derivatives and their rates of change. So example one, we're going to talk about an application to medical treatment, which we call radioactive half-life. So a radioactive isotope of gold, gold 198, is used in the diagnosis and treatment of liver disease. Suppose that a 6 milligram sample of gold 198 is injected into the liver and that this sample decays to 4.6 milligrams after 1 day. Assume the amount of gold 198 remaining after t days is given by the function n of t equals n naught times e to the negative lambda t, where n naught is the original amount and lambda is the disintegration constant for the substance. Basically, it's just a constant that indicates how quickly this particular substance disintegrates. And lambda is going to be the same for gold 198. And gold 198 has a specific disintegration constant. Every type of radioactive substance that you have is going to have a different one. So it's asking us to determine the disintegration constant. So it's asking us to solve for lambda. So to do that, we're going to use that formula. N of t equals n naught times e to the negative lambda t. So we need to pick out some information before we can do that. We're going to need to know n of t, we're going to need to know t, and we're going to need to know n naught. So let's look at our problem here. We said that a 6 milligram sample is injected. So that means that originally we have 6 milligrams. So that's n naught, the initial value. And we said that we get to 4.6 milligrams after 1 day. So after 1 day, t equals 1, the amount in our system is going to be 4.6 milligrams. So let's plug that information in and let's see if we can solve. So that's going to be 4.6 equals 6.0 times e to the negative lambda times 1. So let's simplify a bit. 4.6 is equal to 6.0 times e, and negative lambda times 1 is just negative lambda. Now, since we have a negative exponent there, let's just take that and we're going to flip that into the denominator. And now we can multiply that up, and that becomes 4.6 e to the lambda is equal to 6.0. And now we can divide the 4.6 out, and we get e to the lambda is equal to 6.0 over 4.6. So now we're getting close, but we need to get rid of that exponent. So we need to solve for that exponent lambda. So we're going to use a little trick that hopefully you remember from the last lesson, where we just take the natural log of both sides. But what happens is, remember, according to our log rules, if we have an exponent inside the logarithm, we can move it out front and it becomes lambda times natural log of e equals the natural log of 6.0 over 4.6. And of course, we know that natural log of e is just 1, so that natural log of e cancels. And so lambda is just going to be, you punch natural log of 6 over 4.6 into your calculator, it should get somewhere around 0.266 as your disintegration constant. So for gold 198 in this person's bloodstream, it's always going to, that constant is going to indicate how quickly the amount is dissipating. If it's higher or lower, it's going to have an impact on how quickly it's going out of the bloodstream. The next question is asking us to determine the half-life of gold 198. So in this case, if we start with 6, we're trying to find the time where we go down to 3. So that's going to be 3 for n equals t. And of course, n naught still stays at 6. And we're trying to solve for the time. And of course, we know the disintegration constant now. It's 0.266, which we solved in the last part. So let's plug that information in. So equal e to the negative 0.266t. We can move that 6 over, and it becomes 3 over 6 equals e to the negative 0.266t, or 0.5 equals e to the negative 0.266t. And again, we can use that logarithm trick to try and get rid of that exponent. So take the natural log of both sides. That's going to be natural log of 0.5 equals the natural log of e to the negative 0.266t. And we said that with natural logs, or with any logarithm actually, you don't have to use natural logs, but it just makes the calculation a bit easier because we can get rid of that natural log of e. But with any logarithm, if we have an exponent, it moves out front. So that becomes the natural log of 0.5 equals negative 0.266t times the natural log of e, which cancels because we have natural log of e is 1. So then we can just move that negative 0.266 over, and it becomes t equals natural log of 0.5 over negative 0.266. Or we get t equals roughly 2.6 days. Next part is asking us to write an equation that gives the amount of gold 198 remaining as a function of time in terms of half-life. If you want, remember, think back in the last lesson we talked a bit about switching bases with our exponential growth problem. We could use that same method, or we could just use a bit of know-how about exponential functions. And we could just say the initial value for this is 6 milligrams. The decay rate is going to be a half because it's going down by a half every time. And then the exponent is going to be the number of doubling periods. And so the way we find that is we just take the time and we divide by 2.6. So that fraction there is going to represent how many doubling periods we have. If we've gone 2.6 days, then it becomes 1 doubling period. If it's 5.2 days, then we're at 2 doubling periods, and so on and so forth. So that equation is going to represent the amount of gold left in the system. And the last part asks, how fast is the sample decaying after 3 days? Of course, you should know that when you hear how fast, that's rate of change. So you should think derivative. So we're just going to take the derivative of that function. We can take either function, but since we like stuff with base e when we're doing derivatives, let's use that one. So n of t is equal to 6 times e to the negative 0.266t. So if we take the derivative, it's going to be, let's see, it's going to be, we'll have to use chain rule for this one. That's going to be 6, the derivative of the outside function is 6e to the u, or 6e to the negative 0.266t, and then multiply it by the derivative of the inside function, the exponent. That's going to be negative 0.266. So you multiply that with that negative 0.266 with 6, and we get negative 1.596 to the power of e, times e to the power of 0.266t. And lastly, we said we want how quickly it's going after 3 days. So we want the derivative at t equals 3. That's going to be negative 1.596 e to the negative 0.266 times 3. You can plug that into your calculator, and it becomes about negative 0.72 milligrams per day. So after 3 days, there's about 0.72 milligrams leaving the person's bloodstream each day, and that's going to go down as time passes. So example 2 is all about shock absorbers. So let's say if you're in a car, there's a device in there that keeps the ride from getting too bumpy. And it just kind of disperses all the shock from when you drive over a pothole or over a speed bump. It just kind of helps to smooth out the ride a bit. It basically just starts a bit rougher, and then it kind of goes up and down a bit, and every time it gets a little bit smoother. So the vertical displacement of a sport utility vehicle's body after passing over a bump is modeled by the function h of t equals e to the negative 0.5 t times sine t, where h is the vertical displacement in meters at time t in seconds. Let's look at the function, just so you can kind of see how this looks. Hopefully, just because it's a bit of an odd problem and you might not be familiar with it. So you notice how we start with a bigger height. It kind of goes up quite a bit, and then it goes down a bit, and then slight increase, and then so on and so forth. So over a very short interval, over a few kind of oscillations here, it's gonna become a very smooth ride. So it's asking us to determine the maximum displacement of the sport utilities vehicle determine when the maximum displacement of the sport utilities vehicle's bodies occurs. And determine the maximum displacement. Can you tell I haven't had my coffee yet? Okay, so when it says maximum displacement, usually that means trying to find this spot here. So we already know where it's going to be, we just don't know exactly what it is. But we know that that's going to be the spot where the derivative is equal to 0. So let's try and find that derivative and see if we can solve for it. So we said h of t is equal to e to the negative 0.5 t times sine t. So to find the derivative, it looks like this is going to be a product rule problem. So we're going to take the derivative of each function and multiply it by the original function of the other. So let's start with, let's just write that out just to make sure we're clear on this. So we're going to take this part, and we're going to take the derivative, multiply it by sine of t, and then we're going to take e to the negative 0.5 t and multiply it by the derivative of sine t, just in case you're a little rusty on product rules. So the derivative for e to the negative 0.5 t, we need to use chain rule on that bit, so that's going to be the derivative of the outside function, which is e to the t. And then we're going to multiply it by the derivative of the inside function. And sine of t. And then we're going to do e times e to the power of negative 0.5 t. And then we're going to take the derivative of sine of t, which is just cos of t. So now let's see if we can simplify this a little bit. Let's see. We have an e to the negative 0.5 t that we can factor out of both of these terms. And then we're left with negative 0.5 sine of t plus cosine of t. So we know that we're multiplying these two things together. So if we set it equal to 0, we can just set both of those terms equal to 0, just like with factoring. 0 equals e to the negative 0.5 t, and 0 equals negative 0.5 sine of t plus cosine of t. So let's try and solve here. If we solve for the first one, we can use that trick where we try and take the natural logarithm on both sides. But we know that we can't do natural log of 0. So as it turns out, there's no solution for this one. So we can't find a maximum for this part here. So we're going to have to see if we can find something for the other one. So let's try and solve a bit. Let's start by moving this over. So negative 0.5, that's going to be positive 0.5. Sine of t is equal to cosine of t. But here's where we're going to use a little trick. So what we're going to do is we're going to divide both sides by cosine of t to move it over. So 0.5 sine of t over cosine of t. Hopefully you're seeing what I'm doing now. So we're just going to have 1 left on that side because we just divided it out. It's going to be cosine of t divided by cosine of t. So that's just going to be 1. So lastly, we're going to divide out both sides by 1.5. And on the right side, 1 divided by 0.5 is going to be 2. And here's a little trick. Think back to trig identities. We said that sine over cos is going to be equal to tan of t. So we're going to have to define t. We're going to take the inverse tan of 2. And we know there's multiple possible answers for this. In fact, they're going to represent all the maxes and mins of this. But the first one is going to be 1.1, and so on and so forth. But in this case, we already know that the first one is the important one. That's the big maximum according to our graph. So that's going to be the big one. So we're going to say the rest is inadmissible. And we're going to say 1.1 seconds is our solution. So we found when that maximum displacement occurs. Now we just need to figure out what the actual displacement is. So displacement we just find using our original function because the derivative tells us the rate of change, not the actual displacement itself. So that's going to be e to the negative 0.5 times 1.1 times sine of 1.1. And that, by the way, that's in radians. And that's going to be 0.51 meters. So I'm almost out of space here. But therefore, the maximum displacement of 0.51 meters occurs after 1.1 seconds. So that is the last official lesson of the Calculus and Vectors course. Congratulations. Give yourself a pat on the back. Make sure you do a few practice questions. And that's it. Congratulations.